I'd like to continue my introductory remarks with a few more comments about the reference handbook. Here is the table of contents, and as you can see, it begins with a discussion of units, which I'll talk about in a minute, then conversion factors, then ethics, safety, etc., and a number of topics related to the knowledge areas. However, this table of contents doesn't correspond to the list of knowledge areas, the 18 knowledge areas which I mentioned exactly. There isn't an exact correspondence between them. For example, there's no section here specifically on hydraulics and hydrologic systems. Instead, many of the topics in hydraulics are found within fluid mechanics, and the topics in hydrologics and hydrologic systems are contained within the sections on fluid mechanics and civil engineering. So the topics, particular areas, are scattered somewhat throughout the manual and, as I mentioned before, somewhat hard to find sometimes. Basic to all of this is the idea of dimensions and units, the first section in the handbook. And the first thing that's important, of course, is that any physically realizable equation must be dimensionally homogeneous. And what that means is that all additive terms in an equation must have the same dimensions. To give a simple example, consider the distance traveled by a particle. Let's suppose I have a particle which starts out here, and it's moving downwards at some velocity v0, and we'll suppose that it's subject to gravitational acceleration of magnitude g. After some time t, let's suppose that this particle has fallen a distance d, and the question is, what is the relationship between the distance d and time? Well, that's a very easy problem in kinematics. I'm sure you can do that. And the answer is d, the distance, is v0t plus 1/2 gt squared. Now, in this equation, on the left-hand side, d is obviously a distance, it's a length. v0 times t also has dimensions of length, and gt squared, I'll leave you to put that, also has dimensions of length. So each term in this simple equation has dimensions of length. They're all the same. And that must always be so. If you have an equation where the dimensions of the different terms are different, then there's something wrong with that equation. Now, generally in fluid mechanics, civil engineering, we'll be dealing with three primary dimensions, either mass, length, and time, which we denote by ml and t, and we usually place within square brackets to denote that we're referring to dimensions in that case, and also possibly F, force. However, force is not a fundamental dimension, because force is related to mass and acceleration by Newton's second law, F equals ma, from which you can see that the dimensions of force must be the same as the dimensions of mass multiplied by acceleration, ml t to the minus 2. So there are three fundamental dimensions involved here, either mass length and time, or force length and time. You can use either one, but not both generally. All other physical variables that we're interested in can be expressed in terms of these three primary dimensions. For example, acceleration is length per time squared. Density is mass per unit volume, or ml to the minus 3, etc. For all of the other variables here, power, energy, etc., are all expressible in terms of three fundamental dimensions. And generally, we'll mostly be using the MLT system. However, equally, you could use the FLT system, but not both of them at once. An example then is speed, is distance over time. The fundamental dimensions are LT to the minus 1, but the particular units you use depends on the unit system you're using. For example, the units might be feet per second, or meters per second, or miles per hour. This is the section on units, and if I can just expand, blow up the first part here, it says that the FE exam in this handbook use both the metric system of units, in other words SI, and the US customary system, USCS. So it's important to be familiar with both systems of units to successfully answer the questions. Now, more generally though, there are three main systems of units that are commonly used in engineering and science. And the difference between the two we can illustrate by means of Newton's second law again, which I'll generalize by putting a constant of proportionality. So instead of F equals ma, I'll write F equals kma, where k is a constant, and the value of that constant depends on what particular system of units you're using. So firstly, the metric system, or SI units, we put k equals 1, and we define 1 Newton as the force which gives an acceleration of 1 meter per second squared to a mass of 1 kilogram. So the fundamental unit of force in metric units is the Newton, and the fundamental system of mass is the kilogram. The second one, the so-called US customary system, puts k is equal to 1 over gc, where gc is the universal gravitational constant, which has a value of 32.174 units of pound mass foot per pound force second squared. So in this case, we define 1 pound force as the force which gives an acceleration of 32.2 feet per second squared to a mass of 1 pound mass. So the unit of force here is the pound force, and the unit of mass is pound mass, with subscripts F and M attached there to differentiate between the two. There is a third system, so-called British gravitational system, which also puts k equals 1. And in this system, we define 1 pound as the force that gives an acceleration of 1 foot per second squared to a mass of 1 slug. So in this system, the unit of force is the pound, and we don't really need to put an F on the end there to distinguish it anymore. The unit of force is the pound, and the unit of mass is the slug. But here, as I mentioned in the FE exam, we use predominantly the first two of these. So these are the basic units in in those three systems. The unit of mass in SI is kilograms, USCS is pound mass, and BG is slug. Length is meters, feet, and feet. Time is seconds, and force is either newtons, pounds force, or pounds. Now, different disciplines tend to use different systems. For example, I think that mechanical engineers and chemical engineers tend to use the pound mass and pound force system, whereas civil engineers and aerospace engineers tend to use the slug and pound system. So we just have to be aware of the differences between these. So one way to remember that is that a slug is approximately 32.174 pounds mass, and the Newton, which is not generally a familiar unit, a Newton you can think of as of order of 1/4 pound. There are a few special units that come up. For example, pressure is a normal stress or a normal force per unit area, so it has dimensions of force over area. In metric units is newtons per square meter would be the fundamental unit. However, we usually give that the special name of a Pascal, abbreviated PA. The Pascal, however, is a very small unit, so more usually we use 1,000 pascals or the kilopascal as a unit of pressure. Power is rate of doing work, or force times distance over time, for example, Newton meters per second. But again, this is given a special name. A Newton meter per second is a watt. Another one that comes up sometimes in fluid mechanics that we'll encounter is absolute viscosity. And the units of viscosity in metric units are Newton seconds per square meter, but this you will sometimes see given as a Pascal second, abbreviated like this. The handbook also gives a list of conversion factors, and here I'll just expand on a part of that. But generally speaking, I don't think we need to be concerned with that. For example, converting acres to feet or miles to meters, etc., because generally all of the problems will be given in one system of units with the properties given. So although the conversion factors are given here, I don't think they're a concern for the exam. So here again is the outline of the book. We have units, conversion factors, etc. And let me do an example to illustrate how the units of mass and force work. So here's a simple example. We have a sphere which weighs 5 kilograms, and it's suspended, say, from the ceiling by a cable. And obviously there is some tension force in this cable to hold it up. So the question is, if the acceleration due to gravity is given, the tension in the cable is most nearly, well, which of these alternatives? So that's fairly simple. The tension in this case must be just equal to the weight of the sphere, which is hanging downwards, for that to be in equilibrium. And the weight of an object is just the force of gravity acting on that object, is the mass multiplied by acceleration due to gravity. So in this case, the mass is 5 kilograms, gravity is 9.81. Multiplying those two together is 49.1, and the units in that case automatically work out to newtons, because we've been consistent between kilograms in this case. So the answer is C. Secondly, the same problem, but now we have a sphere of 5 pounds mass, which is hanging from this cable, and the acceleration is 32.2 feet per second squared. The tension in the cable is most nearly which of these? So here again we have the same basic equation, that the tension is equal to the weight of the object, which is m times g. However, now we have to be careful. Because of the units here, we have to divide that by gc, the gravitational constant. Substituting in, we have 5 pounds mass times 32.2, the acceleration due to gravity, divided by the universal gravitational constant, which I'll round off to 32.2, and has units as shown. And as you can see here by checking the units, pounds mass, pounds cancels, feet cancels, second squared cancels, leaving me with an answer of 5 pound force, which of course we would intuitively know. So the answer in that case is 5 pounds force. So this is just an illustration of where you have to be careful with the units when you're using the US system. This concludes my brief overview of the exam and some issues involved with units, and beginning next time we will start a detailed review of the technical aspects of the different knowledge areas.